research being at T.J. Watson in New York. And I'm going to talk about work on storage class memory, and I'm going to give some background on what storage class memory is, a description, and just a little bit on the technology that's used to implement it. And then I'm going to talk about some work that I'm actually involved in. I'm in computer science in the storage specialty of computer science. So I work with disks, tapes, file systems, archive stuff. I've been in storage at Almaden for almost 20 years now. It's really hard to believe. And so this is work that I've been working on having to do with how file systems might change with the advent of storage class memory. And it's actually some ideas that we worked on last year that I'm actually working in collaboration with Samsung in Korea and Hanyang University in Seoul, Korea, on maybe implementing some of these ideas on some very leading-edge prototype hardware. So I've got a lot to cover, and probably I won't get through it all. I'm sure that everybody is familiar with the idea that we have a lot of different kinds of memory in a computer system, and that there's a huge disparity in how long I/O operations take on different kinds of memory. So down here in level 2 cache, we're talking 10 nanoseconds. DRAM is about 6 times slower than that. Flash devices are a couple of orders of magnitude up for reading and a couple more orders of magnitude up for writing. That's the kind of flash drives that most of us carry around these days, including the one I've got in my pocket. Disk drives are another order of magnitude to read or write or close to it. And then tape actually isn't as bad as it looks here, because tape really what they're doing is talking about positioning and reading or writing. Tape actually has very high data transfer rates if the tape's already positioned where you want it to be and it's already moving. But if it's stopped or you have to move it, it can be pretty darn slow. Interestingly, these are orders of magnitude here. This kind of is an indication of, well, if 1 second is, if we think of it in human times, if a CPU operation is 1 second, then reading DRAM from memory, reading from DRAM memory is about a minute. Reading a flash drive is somewhere between an hour and a day. Reading a disk is more like a month, and reading from tape is more like a century. So that just gives you an idea of the difference in magnitude of I/O times that we're talking about. And what I'm going to be talking about today is a new kind of memory called storage class memory that sort of fits in here. Much, much faster than today's flash, maybe an order of magnitude or so slower than DRAM today, but having many of the attributes of this kind of memory and being persistent, which is, of course, what DRAM is not. So what is storage class memory? Oh, wrong way. What is storage class memory? It's a new class of memory device that can be used as storage, and I'll talk ever so briefly about some of the competing technologies for storage class memories, but there are many that are currently competing to be what will be the first real generation of storage class memories. Storage class memories don't exist in the real world in any large way today. They're a research topic, not something that you can go out and buy, but we think they're a couple of years away. So storage class memory blurs the distinction between what we typically think of as memory, which is fast and expensive, but volatile, and storage, which tends to be much slower, considerably cheaper, but persistent, and persistence in general is a very good thing, right? So storage class memory, on the other hand, is non-volatile, which means you can keep data on it for a long time, has order of magnitude DRAM-like access times, has a low cost per bit, more like disk. Currently, it's rather expensive, but our belief is that in another 10 years or so, it'll be on the order of disk-like cost. Today, of course, it's just in laboratories, and it's very expensive. And of course, it's like a flash. It's solid state, has no moving parts, and therefore is very resistant to things like shock and very portable and that type of thing. So a little bit of terminology then. Storage class memory describes a technology, not a use, and I'm going to be talking in the second half of the talk about potential uses of storage class memory in a computer system hierarchy. Flash is not quite storage class memory. It has some of the attributes of storage class memory, such as persistence and no moving parts and low cost. The problem with Flash is, as you saw from that first chart that showed timing, it's incredibly slow compared to CPU operations, and therefore couldn't be used as in place of main memory. However, we are seeing systems these days that are using Flash. It's still faster than disk drives, so we're seeing systems today that are using Flash memory as caches for hard drives, but in terms of replacing the large chunks of the storage hierarchy, Flash isn't doing that. It's being used to augment that, and we'll see that actually in another slide or so. NVRAM is a term you'll hear thrown around a lot, and that just means non-volatile RAM. It simply means random access memory that you can take the power away, and when you come back, the data's still there. Storage class memory is an example of NVRAM, and other types are battery-backed dynamic RAM or dynamic RAM and disk combinations where the disks actually provide the persistence. So Flash is not considered, Flash is a non-volatile RAM, but it's often referred to as a non-volatile RAM, but it doesn't have the random access times that we're looking for storage class memories. Another term, of course, is solid-state disk, and if any of you have a new small Macintosh, you might actually have a solid-state disk in there. And solid-state disks are basically just packaging a bunch of non-volatile memory, today mostly Flash, into a package that looks like a disk drive and behaves like a disk drive and has better access characteristics in some ways. So solid-state disk is a use of NVRAM, and storage class memory is a different example of NVRAM. So if we're going to come up with this new kind of memory called storage class memory that fits in a different place in the hierarchy, where would we probably use it? Well, we would probably start off using it in big data centers. In fact, the first project that IBM Research is working on to use storage class memories is for a very large high-performance computing application that we're working on with the U.S. government, where I have some backup slides I doubt I'll have time to get to. It talks about the problem, the crisis really, with growing disk storage to the kinds of sizes that the government needs for some of these projects because of the power and cooling requirements of disk drives. So we're looking at storage class memory because it's much lower power and it isn't hot like a disk drive. So start out here and probably jump over to portable devices like your iPhone and your laptop, where you care about things like very low power utilization and both in terms of driving the memory itself, but also in terms of cooling the entire environment. And of course here, you also care a lot about making sure that things are shock resistant, so when you drop your phone, as I do daily, you actually don't lose your memory. Probably, look at that wonderful desktop. Probably none of you remember those. Probably not talking about it getting into the average desktop very soon, where hard drives are actually fairly well suited. There aren't really the power problems there. So what's the evolution kind of the use of potentially using storage class memory? So in the old days, really old, 1980, right? You had your CPU that talked to random access memory, and there's fast synchronous I/O here. And then the next thing that you would go to after you went into main memory was a disk drive, and maybe you would even wind up putting data on tape. And so we refer to the disk as archive storage, which is kind of different from archival, but archive meaning you can go away and come back and the data's still there, right? So this line is kind of, anything here, you turn off the power, it's gone. Anything here, you turn off the power, you come back, it's still there. So in today's environment, in very high-end systems, we're starting to see another layer in here, which is flash memory in the form of solid-state disks that may either complement traditional hard disk drives as cache, or in the case of, as I say, some very high-end modern laptops may replace a hard disk drive entirely. We think that in another 5 years, actually these slides we did last year, so it's 4 years now, in another 5 years, we may see this layer replaced by storage class memories, and you'll notice that the storage class memory has gotten to be much larger, so it actually has started to push DRAM aside. So you might have actually smaller amounts of RAM than you're used to having today, because this is now accessible in the same kind of order of magnitude of access time as this, but is persistent. You might see a growth to storing a lot more information here, and using disk as a much less heavily used back end for archive. And then the question that I'm going to be bringing up in the last half of the talk is, in 10 years, will disk drives go away altogether? Will we have reached a point with storage class memories where we no longer need spinning disk drives? And people have been, of course, people have been talking about the demise of tape for 20 years, and it still hasn't happened. And people talk about, but don't actually predict, the demise of spinning disk drives. But if you think about it, the spinning disk drive is a 50-plus-year-old technology, and actually surprisingly few technologies in the computer industry have lasted 50 years. So we have to believe there will be an end to it sometime, and so we're kind of positing that maybe this is what's going to be the end of the disk drive. So what I'm going to be talking about at the end of the talk is, if the world looks like this, what does that mean to things like file systems and I/O subsystems? So there are many different competing technologies, as I said, for storage class memories. So Flash is, of course, what's out today, and people are working on improving Flash to make storage class memory out of it. But Flash is basically, by its nature, slow, and also has very poor write endurance, which means it has a relatively low number of overwrites of a particular block within Flash before the media is literally worn out and can't be used anymore. And so the kind of flash drives that you carry around with you actually have some microcode for wear leveling on them that tries to spread out where data is written so that you don't keep writing to the same place all the time. So that's kind of interesting. We don't see that actually getting a lot better. So I could have done 2 times the length of this talk just talking about these technologies, so forgive me if I just kind of rush through them. There's a really interesting research going on in my lab. By the way, my lab, interestingly enough, is the lab that invented the disk drive in the 1950s, and we have the original prototype sitting in our hallway. It's just amazing. We have some work going on a memory we call Racetrack, and there's a little picture of it over here. I don't know if you can see it, but maybe you can see these little bands of different colors moving up and down this what we call a racetrack, and there's actually a little meter over here showing zeros and ones. And basically the idea of this is that we've learned how to store multiple bits of data in the space that one bit used to take by kind of having different striations of data in the same cell and putting a current in that forces the striations to move across a read-write mechanism. It's kind of an amazing stuff. It's totally in the lab today, but it's very promising long-term. So that could be a way, because one of the real keys, of course, for something like a storage class memory is not only speed, but also density. You really have to get the bits per cubic inch, if you want to measure it that way, down very, very small so that you can pack a lot of these in a small space. Magnetic RAM, MRAM, is used today, but it's a space hog, and it doesn't. The manufacturing techniques for it don't scale very well. The most promising technology that we have today is called phase change RAM, and phase change is a technology that you probably all have used. It uses a crystalline substrate that can change states based on heat from a crystalline to an amorphous form, and those 2 states have different reflectivity, which is how your rewritable CDs and DVDs work, and they also have different resistance. And so you can both shine a laser beam on this phase change media and tell whether, and see whether the reflection is reflected back or dispersed, and use that to read and write DVDs and CDs. Or you can actually use it inside a chip, and you can measure the difference in resistance. And the nice thing about phase change is once you apply a current to it to change its state, stays in that state essentially forever until you apply a current to it again. So there's a lot of work going on today in putting tiny, tiny phase change modules inside ICs, integrated circuit size packages. So that's kind of what people are working on today for the implementation of storage class memories. We think that some of these really off-the-wall things like magnetic racetrack have some potential. There's also this thing called solid electrolyte that is early in its development, and there's some possibilities. So I have a chart, I don't have it in this deck, that shows all the companies working on building what will be the next great storage class memory technology. There's literally dozens of them. IBM has about 50 people working on it alone. Samsung has a huge, because Samsung I think is the world's biggest flash memory manufacturer today, and so they want to make sure that they keep that leadership in whatever the next technology is, which is why we're working together on file system stuff. A lot of companies you have never heard of, because I've never heard of them. So there's a lot of work going on in this, and it has the potential for being a really big thing and generating a lot of money. So in developing storage class memory, we basically have the traditional conundrum. Oh, sorry. My machine is responding slowly for reasons that I can't explain. We have the kind of traditional conundrum that you have in designing technologies of wanting to have conflicting priorities. So you'd like to have your storage class memory be very fast, you'd like to have it be very cheap, and you'd like to have it have very good write endurance, meaning you can write it many, many, many times without wearing the media out. All three of these things today in today's technology can't be achieved. You can't get all three of them. So we're looking at uses that are memory-like uses, using them in place where you might use DRAM today, and we're concentrating on speed and write endurance for those uses at the cost per bit. Other applications would be more storage-type uses, like replacing a hard drive and having relatively slower speed and not as much write endurance because you don't write a hard drive as often as you rewrite RAM. There's also the issue of power. So as you get more speed, you take more power. So there's these interesting trade-offs, and so people are designing different storage class memory technologies to today address different parts of these markets. Of course, the holy grail is to find something that has all of these attributes. We haven't done that yet. This is a little chart on cost. It's kind of interesting if you look at years. This is the year 985. Looking in the 1980s and 90s, how the cost of disk drives, this blue line, in dollars per gigabyte has plummeted. Then we have NAND in green memory and DRAM in red and these prices. And we see out in the 2010, 2015 kind of a time range, we predict the storage class memory is going to be down here. Now, disk will probably continue to drop as well, but we see these being very competitive with disk. And there's some details about how we get to these different things, but I'm not going to spend too much time on it. So that's a whirlwind introduction to storage class memories, and I would have liked to spend a lot of time on it, but at least you get the idea of what the goal of storage class memory is and the fact that there's a lot of work going on in storage class memories. So now I'm going to change direction a little bit and talk about, okay, let's suppose that it is 2018. Let's suppose that that chart that we saw really comes true and we really have eliminated, for all practical purposes, disk drives out of a lot of systems. How does that change the software that we are accustomed to running either in our servers or our own laptops? Excuse me. So this talk is based on the assumption that relatively fast, affordable, non-volatile memory becomes available in quantities large enough to replace traditional disk drives in a decade, right? And we think that the availability of these memories will enable real changes to the way we treat our I/O stack, but they'll also demand it. We'll have to change the way certain kinds of things are done. in order to talk about this, I want to talk a little bit about something that I'm kind of a specialist in, and that's file systems, because this is what we're going to talk about changing. But I'm going to assume that not all of you are file system specialists, so I'm going to do a little overview of file systems for you. So there are many types of file systems in today's world. There's the local file system, like on my laptop, distributed file systems that you undoubtedly use to access servers here at school. There's clustered file systems for high-performance computing. There's general purpose and special purpose file systems. But all of these file systems have some very similar capabilities and services that they provide. One of these, and the most obvious to us, or the two most obvious actually, are if you're a programmer, there's a programming API that you use. So if you're a Linux programmer or some other version of Unix like Sun OS, you're used to this interface called POSIX, where you do open and read and write and that kind of thing. And if you happen to be a Windows programmer, there's a similar but different API for Windows NTFS, which is kind of the Windows standard these days. So there's this programming API, and there are, of course, millions of programs that have been written to use these APIs. So they're pretty well standardized. We're also, of course, accustomed to seeing a namespace, and that's maybe the thing that we as users at least see the most of, and that's some way that we can name and organize and refer to our files and data sets. So typically what most of us are accustomed to is a directory-based tree structure file system, starting at some root, which might be a drive letter or a slash, and going down through a hierarchy of directory trees. There are file systems like IBM's mainframe file system that have an essentially flat namespace, but one way or another we're accustomed to having a way to name our files and find them. So those are things that are very obvious to us as users, the namespace, and as programmers, the API. There are many things that are done under the covers by file systems that are very important to understand, and one of them is in-memory caching. So caching is, of course, I'm sure you're all aware, is just taking data that might have been somewhere else that's slower and putting it somewhere that's faster to access. Typically, a cache is much smaller than the original source of the data, so you have to be careful about what you put in cache. But once you put it there, you can get to the data much more quickly. And there are caches at almost every level of the processing hierarchy these days. In-memory caching for I/O, for file systems, is basically done for two complementary reasons that are both related to the disparity in memory versus disk access time. So we saw that chart that had access memory here, access a disk drive here, right? And that disparity leads to caching for two different reasons. For input operations, when we read data in off a slow device, we put it in a cache in the hope that because we read it once, we'll be likely to read it again. So that data that's sitting there in the cache may have been read or written earlier. Sometimes there are even prefetching algorithms that say, I think I'm going to want to read that block, I'll put it in cache now so it'll be here when I need it. That's an area of a great deal of file system research, as a matter of fact. I have a couple of friends who got their PhDs on that subject. For output operations, data is cached in order to isolate your applications from the very slow external memory. So if you're if you're running a program, and that program's writing data to disk, you don't necessarily want to wait while each 4K block is synchronously written to the disk and then come back and do some amount of processing. You would not be able to stand to sit at a computer that wrote data synchronously. So data is cached when you do a write, control is returned to your program, the data is flushed to disk sometime later, often by a background task. This can be problematic, of course, because if you haven't flushed your data to disk, and this is a big trade-off that we all make in our daily use of computers, is we trade reliability for speed by saying, yes, I'll let the file system cache data that really I want to make sure is on the disk, but I really don't want to wait for it, so I'll let it cache it, and I'll just keep my fingers crossed that it gets flushed to disk before my next blue screen. So this can be problematic. System failures can lead to inconsistent data, and in the worst case, that can lead to corrupted file systems, although most modern file systems do a form of journaling that keeps that to a minimum these days. So both of these reasons for caching are problematic, especially when data is shared across multiple systems. So in a distributed computing environment where you have shared data access to storage, both of these kinds of caching lead to a lot of locking between systems saying, well, I can't let you access this block because I've got it cached in my memory, and the other system says, well, I really need to access this block, so you really need to get it out of the cache, and then the system that has it cached writes it to disk and then releases the lock, and then the system that's going to read it grabs it. And it's very complex, it's very error-prone, it's one of the most complex parts of distributed file systems is the locking because of caching. File systems are often very tightly tied to the virtual memory system of the operating system that they're running in. This allows features like memory mapped I/O, so that you can treat a file that you're reading as if it's actually resident in your memory space. But tying the virtual memory system to the operating system can lead to very complex implementations of the file system. And I was involved in a system where we wrote a Windows-compatible file system, and the file system virtual memory system interface is incredibly complex and error-prone, and has these conditions where you can get into access memory, no, I need to go to disk, no, you can't go to disk because of some virtual memory request, and you get into a locked-out condition, and in fact that leads to a lot of the blue screens you've seen. Finally, the thing that file systems do for you is the thing that you really thought they were doing for you all along, is device access, right? After all this other stuff happens, you actually wind up reading and writing stuff from a disk, and that could be a very simple operation. You could simply convert the file offset to a block address on the disk and call the device driver and say, read or write this block. But in modern file systems, even that isn't particularly simple because, first of all, you have to deal with any number of error conditions, and that's I was at a conference recently where there was a paper discussed about how many file systems have so many error conditions that are simply not handled in the file system. This group at a university went through and did like 5 different file systems and looked at all the different error conditions and found that some file systems simply ignore as many as half of the possible error conditions and never report them back to the user of the application. And it's pretty awful. Also, this file I/O may involve doing a read, modify, write. I don't know if most of you are familiar with this concept, but because disks are written in fixed-size blocks, if you want to update a byte of that block, you really are forced to read the entire block, update the byte, and write it back, right? So that's complicated. There may be network accesses involved, or access to multiple devices in some kind of striping scheme, parity computations in RAID 5. So there's all kinds of stuff that goes on even at this low level, which may or may not always be in the file system. Of course, sometimes RAID 5 happens in the controller, but oftentimes it's implemented in the file system. So with that introduction, let's talk about how some of those things might change if we had storage class memory in place of disks. I've already talked about this. So the first thing I'll say is that it's unlikely that the externals are going to change anytime soon. While there has been a lot of research, and I'll talk about it at the end of the talk if I get that far, on changing the way we access data in our computer systems by going to what's called the semantic file system and simply saying, I want the file that meets this English language description without giving it a name. The truth of the matter is that I think most of us are very comfortable and accustomed to accessing data in the directory tree structure, and that's kind of going to stay with us for a while. The API is equally unlikely to change because of these millions of programs that already exist that use them. People are going to be very, very slow to adopt new programming APIs and go back and change programs that exist already to change it to use a different programming API. So my belief is that the internals of the operating system, the levels below the things that you as a user or even a programmer see, are the things that are both likely to change most quickly and the things that might provide the most immediate benefit to go into a new technology. So the first thing we can talk about is this idea of in-memory caching. Sufficiently fast storage class memory will essentially obviate the need for caching. So if the storage class memory is fast enough to allow direct access to the primary copy of the data, so what we're saying here is we don't have a disk drive anymore, we have a storage class memory, our primary copy of our data is in that storage class memory. We may have a backup or an archive of it, further back in the hierarchy. which some people are guessing might be disk, but I think more likely tape. Then this whole concept of having to bring it in off slower media into faster media goes away because your storage class memory is fast enough. This in itself eliminates all of the problems with unprocessed writes and programmed flushes to disk. And because of that, multiple access across multiple systems to the same storage class memory could provide much simpler locking protocols for distributed access to data, and no more concerns about what's called cache consistency, where two different systems might have different cached copies of the same data and you forget which one is the right one. Or you know which one's the right one, but one system doesn't know it. So, so in-memory caching could essentially go away, which would tremendously simplify file systems. So I've only got another 10 minutes, so I'm going to keep going here. Another interesting thing is that storage class memories, unlike today's flash, which by the way are written in blocks like a disk, bigger blocks actually, storage class memories should have no hardware enforced block boundaries. They should be like DRAM. That means that the whole idea of read, modify, write for small updates goes away because you just literally write the bytes that you're interested in. And it also gives us an interesting opportunity to rethink the data structures that we use to implement the file system. So for many years now, the kind of norm for modern file systems has been a B-tree structure for directory structures. But that's because B-trees map very nicely to block I/O access, reading blocks and then having a pointer to the other block, etc. But if you didn't have blocks, if you simply could treat your file as byte-addressable storage, you could have skip lists, Bloom filters, structures with different kinds of behavior than B-trees used to implement some parts of your file system metadata. And this is an area that hasn't really been explored yet. But as we get closer to having storage class memories, I think it could be a really interesting area of research. So the storage class memory could be treated as main memory both in terms of access and in terms of addressing. So what does that mean? Access in terms of just go get a byte or get the bytes you need as opposed to read blocks from a disk and find the bytes. But also in terms of addressing, we could use the virtual memory capability of all modern systems to simply map ranges of our storage class memory to an application's address space. Today, when you do memory mapped I/O, what you really do is you copy pieces of the file into memory and then you map those pieces, or you build a table that says go get this block when I access this memory address in memory. Input operations that map storage class memories read-only could simply be mapped into the application's address space and go out to the storage class memory, and the only thing you do is go through an address translation. Applications that use memory mapped I/O could be extended to output as well. There's some reasons why you wouldn't do memory mapped I/O for applications that didn't use mmap for output, because they might assume that they can change structures in memory, and as long as they don't do some I/O operation, that those changes aren't written to disk, they're just done in RAM, so you have to be a little bit careful about the assumption the program makes about where data is being updated. But in general, you could consider having all file I/O essentially mapped into your memory space of your application. We could think about loading applications themselves as a memory mapping function. So instead of reading an application into DRAM, you just say, where's that application on disk? Map this into my address space and jump to the first byte of that, the entry point of that application. And this is actually, there's a shared read-only memory mapping used in some modern operating systems like Sun OS and AIX Unix today that does something similar to this. It's true that the memory speed might be a little slower in storage class memory than it would be if you brought the whole thing into DRAM, but you've saved the overhead of bringing the application into DRAM, and meanwhile you're going to be filling up your processor cache's working set with the most commonly used parts of the application anyway, and that whole working set concept could totally mask the difference in access for the application. So that's just a kind of an interesting idea. To take this whole idea a little further, if the memory address mappings were consistent, if once you assigned a memory address to an application, you kind of said, well, I'll always assign that memory address to this application. And by the way, this gets back to old operating systems like CPM, where the applications always started at exactly the same address, and you could actually have built-in tables of data inside the application that you knew were always based at the same address, something that we don't typically encourage these days. You could, however, have useful both inter-file and intra-file pointers that you could implement and literally have data structures in an application point elsewhere inside that application, or even conceivably into other applications. And you could build efficient embedded data structures in data files, because the data file could always be mapped to the same virtual memory address, and so you could have pointers that didn't have to be resolved at load time, that just pointed to other data structures in the file. So basically what we've kind of gotten to here is this idea that we have this address space in storage class memory. We can map it into our application's address space and treat it like main memory. And so basically what's happened, if we follow that idea then, is that the file systems become really just an interface and a namespace manager for the whole memory subsystem. So you basically just end up with a byte-addressable memory subsystem and a file system that's mapped on top of that imposes a namespace and an API on top of it, which is a very different, maybe not a very different picture logically than we have today, but the implementation would be extremely different. Block extent lists in file pointers would be replaced by memory addresses or memory address ranges. And as I already said, at the lowest level, all files would be processed through memory mapped I/O. Imagine if the storage class memory address space were sufficiently large, 64-bit address space, for example. It might be possible to have files universally mapped to a single contiguous address space, and we could get to an idea that was actually first proposed back in the 1970s called a single level store. And actually there is one system in existence today called the AS400 that implements a single level store, but they do it with a great deal of difficulty. And the idea is that there are in fact no I/O pointers, no such things as disk drives in the file system level. Every object that exists in the system, whether it's a program or a file, what we would think of as a file, simply has a globally unique memory address, and everything's accessed as memory. And you could imagine if the storage class memory address space were large enough, building a system like that and then having a shared memory where you were able to publish through the file system interface, the directory interface, what the address for any particular piece of data was, application or data file, and have multiple applications sharing that same address space and reading and writing to it. So a single level store is an interesting idea that, as I say, has been around for a long time, but has been very, very difficult to implement. But a sufficiently large namespace over a storage class memory could make that a possibility. And this is one of the things that we hope to play with in this little research project I've got going on with Samsung. This idea of a single level store. So here's an interesting question. If your storage is your persistent, is your memory, what we call today RAM, then what would you use a paging or a swapping system for any longer? In fact, paging as we know it would be unnecessary, because the whole idea of paging is to have stuff out on disk and bring it into memory as you need it, and then get rid of it when you don't need it. But if you don't bring it into memory, if it's already in memory, of course, the whole idea of paging goes away. Most pages would never move. They would just sit out wherever they live, and they'd be updated there, and that would be it. And really, the only thing you'd probably use the virtual memory subsystem for is simply this mapping. To map whatever your storage class memory address space was into your application address space. Storage class memories would also have very different failure models from today's disk drives. So I assume at least many of you have studied things like RAID 5 and why we have RAID 5 so that we can have striping across lots of disks so that when one disk fails, we can put a new disk in and rebuild the system and still get to the data. That's not how a storage class memory is likely to fail. There is no such concept as a drive, so the chances are that bits or small ranges of bytes will fail together in the storage class memory, but you're not going to have an entire multi-gigabyte chunk of the storage class memory likely to fail. So we're still going to need the kind of protection and space efficiently that systems like RAID give us today, but the implementation will probably need to be completely rethought. Because it's unlikely that large amounts of data like a disk drive will become suddenly unavailable, and it's more likely to small ranges, we might use things like erasure codes. Erasure codes are ways of storing multiple copies of data that have some redundancy built in, so that there's like 3 of 5 codes where if you have 5 chunks of data, if you can find any 3 of them, you can rebuild the other 2. And there are different kinds of erasure codes that give you more or less protection and more or less overhead, much like RAID. One of the really interesting areas of research that we've talked about a lot at my lab, but I'm now out of time, is trying to figure out how important data is. If you have a file system with hundreds of thousands, millions of files on it, it's a given that some of that data is going to be more important to a business or even a person than some of the other data. And one of the things we'd like to figure out how to do, but still really don't know how to do, is tell the unimportant data from the important data. But if we had a way to do this, we could start doing, today if you put data on a RAID 5, it gets RAID 5 protected whether it's important to you or not. If we use this erasure code kind of thing and we could understand the importance of data, we could actually have different erasure codes or even no erasure codes for different files based on their importance. And so we'd replace the indiscriminate use of RAID by something like this. And I've only got one more slide, and it is simply to talk about the idea that we could also look at starting to implement new storage paradigms like semantic file systems in a storage class memory, because we have this ability to have things like intra-file pointers and a very different kind of data structure than we have today. And I'll make sure that you all have a copy of these slides and you can go back and read this. But since we are out of time and George has told me that he would be doing this, I'm going to stop here and maybe have time for a question or two.
Okay, one question.
Yes?
What's the Bloom filter?
What's a Bloom filter? I would refer you to a computer science course. But a Bloom filter in general is a way of having something like maybe a bitmap that allows you to say, that allows you to do a very quick check and say whether a particular, let's say, piece of data could match a particular criteria by creating this bit vector and turning on bits in the vector that are basically the location of which are determined by some hashing algorithm or something. That says, if this is true, turn on this bit. You might have more than one thing turn on the same bit. If you go to that bit and it's not true, you know the condition can't be true. So it's a very quick way of having a first level filtering to say whether a condition could be true or not.
Okay. Well, thank you very much.